A true understanding of theories and equations often comes with an understanding of where the equations themselves came from. So in this video, I'll be introducing you to simple beam theory, and I'll be deriving the bending stress equation that was introduced to you in the previous video. So we now have some understanding of bending in beams and bending moment diagrams, and we understand the form of the bending stress. But how did we come up with the equation stress is equal to my on I? Well, we did so using simple beam theory. Simple beam theory is also called Euler-Bernoulli beam theory, after the pair who developed it in 1750. The theory, however, reached prominence only after 1899, when it was used to design the Eiffel Tower. So how were structures built before 1899? Well, rules of thumb, in fact, constituted almost the whole body of engineering theory. The old master craftsmen only had their experience and those of others to go on, and such experience got laid down in rules such that a dome would be unlikely to collapse if built to certain proportions. And if things did fall down, it wasn't because they were bad craftsmen. It was usually put down to being an act of God. So moving on, the assumptions of simple beam theory are: 1. A beam must be long relative to its depth and width, and thus stresses developed perpendicular to the beam length are much smaller than those parallel and can be ignored. So those parallel stresses I'm talking about are our bending stresses. Assumption number 2, the beam cross-section is constant along its length. Assumption 3, the beam is symmetrical about the YY, this axis here, resulting in no twisting or torsion occurring. Assumption 4, deflections or deformations are small, which they usually are in beams. 5, the material used is isotropic and obeys Hooke's law, and we know most materials such as steel and concrete, aluminium are all linear elastic in their elastic region. And finally, assumption 4, plane sections remain plane. So when a beam bends, we assume its cross-section, which was originally linear, remains linear. Now, real-life structures never meet these assumptions exactly, but usually approximate them well enough for the theory to be fairly accurate. In practice, many engineers forget these assumptions and often apply the theory inappropriately. However, the conservative nature of structural design, having load factors of 1.2 on dead load and 1.5 on live load, often compensates for this, and thus structural failures due to design very rarely occurs. So moving on, simple beam theory involves consideration of the type of material, the way the beam deforms, the geometry of the beam, and in the internal equilibrium. When talking about the type of material, we mean what modulus it has, which is a measure of the stiffness of a material. Now we know beams curve under load, so what actually is curvature? Well, curvature is the rate of change of the beam slope, and the slope at a point is the value of dy dx. However, using one of our assumptions that deflections are small, tan theta can be approximated as theta. And when done so, theta is considered in radians, not degrees. So looking now at a beam bending, curvature is the rate of change of the slope, and now we call slope theta. So in this image here, at point P, we have a beam slope of theta, and at point Q in the beam, we have a slope of theta plus d theta. And curvature, being the change in slope here, is equal to theta plus d theta minus theta, divided by the distance between the 2 points, ds. Now, assuming plane sections remain plane, our sixth assumption in simple beam theory, our deflected shape follows that of a circle. And we know for a circle that our radius times our angle will be equal to our sector length, ds. So thus, rearranging this formula here, d theta ds is equal to the inverse of our radius, and thus now we have a relationship between our radius, our curvature, and our slope, theta. So what do we do this information? Okay, we've defined our curvature as d theta ds. Consider over here a section in our beam curving. At the neutral axis line here, our length is delta x. And at a distance y from the neutral axis, we want to know what the strain is. And strain being the change in length divided by the original length, we would define strain to be our delta theta dashed, take away our delta theta, divided by our original length delta theta. Now once again, looking at sectors in circles, we can define here r times delta theta to equal delta x, and r plus y times delta theta to equal delta x dashed. Putting those values now in our formula, we get a value for our strain in terms of y, the distance from the neutral axis, and the radius or the curvature. Now bear with me a little bit longer. If we know strain is equal to curvature times y, then using our stress-strain relationship, we now have an equation in terms of stress and our modulus, our curvature, and our y, distance from the neutral axis. Now for a small element here, dA, in a cross-section, force due to the bending stress, dF, will of course be equal to the stress acting on dA. And if we want to know the value of the force acting on the cross-sectional area, that's equal to the integral of the stress acting on our area. And instead of stress now, we can write our newfound expression, Young's modulus times curvature times y. So, what next? Well, for any given section, integrating the area above or below the neutral axis gives us the total compression or tension force in that region, as shown here. Of course, there are no net axial forces, as all the forces in the x direction equal 0, and thus those two forces together sum up to 0. However, the two forces create a couple or a moment, as they are parallel but not in line. And it is that moment that is, of course, the internal bending moment. And taking moments about the neutral axis yields the following equation, where moment is equal to Young's modulus times curvature times the integral of y squared dA. Now this integral is what we have previously been introduced to as the second moment of area, called the second moment because of the y squared value here. This equation is the Euler-Bernoulli equation, and it is this equation which is used to calculate deflections. You will be doing that if you continue on with civil eng, but we'll continue now to our bending stress equation. So here's our Euler-Bernoulli equation, our relationship between moment and curvature, and here is an equation we derived along the way between stress and curvature. Rearranging equation 3 and substituting it into equation 1 yields the equation we want. Stress is equal to my on I. And it is this equation we use to design all our beams. Thanks for listening.